This is a lecture for Chapter 6 on completing the square. For the conic sections in Chapter 6, we had two ways to write the equation that describes the conic section. One was the standard form with A's, there'll be no B's, of course, C, D, E, and F, and G. Okay, and the other was a graphing-friendly form that included the center of the figure, H and K, and other factors such as the A and B, for example, that gave you the lengths of the major and minor axes in the ellipse, or the R, which was the radius in the circle. So we like the graphing-friendly form, but we might be starting with the standard form. From the results above, we could pick out from the standard form, depending on the values of A and C, we can decide that this is an equation for an ellipse, a hyperbola, a parabola, or what did I miss? Circle. Okay, we can decide it's that, but we don't know where the center is, we don't know the radius, we don't know the major minor axes, we don't know anything about it. But we can move from the standard form to the graphing friendly form and find out all that information by completing the square. First, I'm going to review what a perfect square is and how we can use a perfect square to solve an equation. This is considered a perfect square, a plus b squared or a minus b squared. When you expand these forms, remember you have to FOIL. You can't just write a plus b squared equals a squared plus b squared. There's a list up in Fairbanks in the math department of the of unforgivable errors, and this is one of them. You can't do this. There's other lists around in math departments in other places too that have lists of unforgivable errors, and this is always included in them. When you have this situation, you have to FOIL, and when you FOIL, you get a result such as this, or if you have a negative sign, you get a squared minus 2ab plus b squared. Here are some examples of perfect squares, and from this we're going to find a pattern. X plus 4 squared becomes x squared plus 8x plus 16. X plus 5 squared is x squared plus 10x plus 25. And then for the minus 7, I have minus 14 plus 49. There's a pattern here. In the first one, 8 is 2 times 4. Here's the 4. And 8 is 2 times the 4. And the 16 is 4 squared. The same holds here. 10 is 2 times the 5, and the 5 is what's right here in the parentheses. And the 25, of course, is 5 squared. And when we get to the minus 14 is 2 times minus 7. The plus 49 is minus 7 squared. Now this is just a review on how we use the idea of a perfect square to solve equations. If I had this equation, x squared plus 10x plus 25 equals 100, I can write this as the perfect square, x plus 5 squared, and then just take the square root to solve the equation. So we're going to be doing something similar for the conic sections. But sometimes we start off with an expression like this, in which the left-hand side is not a perfect square yet. So we're going to force it to be a perfect square as follows. We'll use that pattern that we saw before. First, you need to have the coefficient of x squared 1. If it isn't, you have to divide out the number. If there's a 2 there, divide by 2 or whatever. But here we just have the 1 there, so we're okay. We take the whatever's multiplying the x, the 10, the coefficient of x, divide by 2, and that'll give me 5. Take the 5 and square it and get 25. So we add 25 to both sides. And this is the result. On the left-hand side, we have x squared plus 10x plus 25, which is a perfect square. We could write it like that. On the right-hand side, we also had to add the 25, and we ended up with 100. So that's how we force an equation to, into the pattern of a perfect square. Here's some of the rules. If we have a coefficient of x that is not 1, we divide the equation by whatever that number is, so that the coefficient of x is the invisible 1. Here we had 6x squared plus 18x equals 54. Dividing everything by 6, we get x squared plus 3x equals 9. The next step, some people don't do this, but I always do this. The constant, I always move to the right-hand side. So on the left-hand side, you just have an x squared term and an x, or perhaps also a y squared term. and a y. But the constant is over here on the right-hand side. In the next step, once you have all that done, you take the coefficient of the x, divide it by 2, and then square it. That's the number you add to both sides. Be sure you add it to both sides. So in this case, we had to add 100 to both sides, so here's the 100 on both sides. This procedure created a perfect square on the left-hand side, and you still have that constant on the right-hand side. And on the slide I've listed again the goal. The goal is to take the standard equation for your ellipse or hyperbola and change it into the graphing friendly form so you can pick out the center and draw the conic section. This is an example. In the end we'll have an ellipse with a center at -3 and 0. The major axis, half the major axis squared is 29, half the minor axis squared is 4.833. But we don't know that initially because all we have is the equation in standard form. We can determine that it is an ellipse. In this case, A is 1, C is 6, neither one are 0, and they're not equal to each other. But the signs are the same. So this is an equation for an ellipse. So we can pick that off, but we don't know the center, we don't know any of the dimensions of the ellipse. But we'll find that out by completing the square. So what we do is, first we're going to take the constant, oops, let's get another color. So we're going to take the constant, which is -20, and put it on the other side. In this case, we've got two variables, x's and y. So put the x's together. So here the x's are together and the y squared. There's nothing to do with the y squared, just leave it alone because there's no y term. But the x will need another term to make it into a perfect square. So we do the same procedure as before. We take the 6, we divide by 2 and get a 3. We square the 3 and get a 9. This is added to both sides. So we add it to the left-hand side here and to the right-hand side over here. We end up with 29 for the constant. On the left-hand side, this term is a perfect square, x plus 3 squared, so we write it that way. Now we've done all the work and just rearrange. Divide both sides by 29. Alright, to get a 1 on the right-hand side, remember the standard equation for the ellipse is x minus h squared over a squared, assuming a is bigger than b, y minus k squared over b squared equals 1, and we want that form. So here we've got the 1 on this side by dividing the 29 out. X plus 3 in the form x minus h, then h would have to be minus 3, so we found that out. We have y squared, it's y minus k squared, so k is equal to 0. And then here's the a squareds as mentioned above, and the b squared. In the second example, we'll have to complete the square on both x and y. It will become a rectangular hyperbola. A squared and b squared are the same, and the center is at, it's missing a parentheses it looks like, center is at negative 0.75 in x and 1.5 in y. But we again start out with the equation in standard form. Okay, so here's the equation in standard form, and we know it's a hyperbola because a is not equal to 0. In fact, it's equal to 4. C is equal to minus 4. The signs are different. They're non-zero, and the signs are different. Therefore, it's a hyperbola. But we don't know the center, and we don't know the dimensions of it. So what we do here is take that constant, the minus 20, and move it to the other side. Then we put the x's together and the y's together. And, of course, we want 1's in front of the x squared and y squared, so we factor out the 4's. We're going to have a little fun with parentheses here. So the intervening step, if you missed that, would have been 4x squared plus 6x, minus 4y squared plus 12y equals 20. But we want these coefficients of the squared terms to be 1. So instead of dividing through, which actually you could in this case, but you, well, no, because you've got the negative sign here, factor out those 4's. Factor out the negative 4 in front of the y, factor out the positive 4 in front of the x. So when I factor it out, I end up, for the x terms, I have x squared plus 1.5x, and for the y, y squared minus 3y. Now we complete the square inside the parentheses. So that means I'm going to take the 1.5, divide it by 2, and get 0.75 and square that. Same with the 3. I take the negative 3, divide by 2, and get 1.5 and square that. And so you'll see that term right here. Here, I added it in here, and I added it here. Now the trick here is that in the other case, we could immediately add that term to the other side, but in this case, because I'm working inside the parentheses, I can't. But if I plus and minus it, that's the same as adding 0 to the equation, so it doesn't matter. In fact, that's the step before that we kind of passed over. So if I add 0.75 and subtract 0.75 inside the parentheses, I haven't done anything, and that's a legitimate operation. Same with the 1.5. If I add in 1.5 squared and subtract 1.5 squared right next to each other, I've done nothing. I've just added 0 essentially, and that's legitimate. Okay. Now, the first 3 terms here are the perfect square. And here's that perfect square right here. Of course, we still have to be multiplied by 4. In this case, these terms make up the perfect square, so I write these like that. The minus 4 is still here. But the 4 gets distributed, in this case, to this term, and in this case, to this term. Alright, and we can see that right here. Well, that was supposed to be a, marker. Right here and right here. Those terms in red move over to the left-hand side. Okay, so now we have 2 perfect squares, x plus 0.75 squared and the y minus 1.5 squared equals 31 1/4. Now remember that the equation for the hyperbola was x minus h squared over a squared. This is a right and left opening hyperbola, k squared over b squared equals 1. To get that into this form, I divide through by the 31.5. Of course, that gets rid of these 4's up here. So you can see that this is a hyperbola. You can pick off the center here. This would be minus 0.75 and 1.5 in y for the center. And now you have the dimensions of the hyperbola. A squared is 7.8125, and in this case, b squared is the same. And the negative sign remains here. It's a parabola that opens to the right and left.